Hello everyone, welcome to STAT 479 Lecture 14. So today we're going to be wrapping up our discussion on the lasso and then the overall topic on regularization. So this was the third module and we're going to be wrapping it up today. And then we're going to start to introduce the next module. Today it'll be pretty introductory on the next module, which is graphical models, and that'll be kind of the last. That'll probably be the last and the the module that probably has the most lectures. But first we'll kind of wrap up our discussion on the lasso and regularization. So we've spent quite a bit of time on this topic of the lasso and L1 regularization because it's a very important topic, and as we've seen in the last couple of lectures, it also introduces another number of key concepts that potentially are new, because we have this L1 norm, which is non-differentiable, and so that introduces notions like subgradients and so on. Okay, so just recall that the lasso regularization, this should be in an element sign here, is just the augment of this lasso, is just the augment of this mean squared error plus the lambda times the L1 regularization. And this is a convex but not a strictly convex function, so any local minimizer is a global minimizer, but the local minimizer isn't necessarily unique. And then we introduced this notion of subderivatives in the previous lectures, which I spent a bit of time covering in lecture 13. And so the subderivative of this is this usual term that we see, x transpose xb minus y. But then we have this plus lambda z. And the z is the subderivative of the L1 norm. So that's going to be plus or minus 1 when b is either bigger than 0 or less than 0. But then at the point 0, which is this point of non-differentiability, there's multiple subgradients, and any number between minus 1 to plus 1 is a subgradient. And so one condition, like we set the derivative to 0, a condition to ensure that beta hat L is a minimizer is that the subderivative is set to 0. And so we can kind of set the subderivative to be 0 here. And one of the things we've assumed throughout that's kind of made these algorithms somewhat more plausible or easier to kind of see what's going on with these algorithms, and it is easy to extend this to general x as well, is that we've assumed that x transpose x over n is just the identity matrix. And then we've set y tilde to be x transpose y over square root of n. And the reason why we do this is because you get this very nice form where you can kind of break things down by coordinate. So, beta hat Lj, so just one coordinate of b hat L, that can be expressed in terms of y tilde j, because remember y tilde is now a p-dimensional vector. So this is in r to the p. And the way we relate them is through this soft thresholding operator. So the lasso does this soft thresholding, which is very useful because in some sense we want to do some notion of model selection here, which means we want some of the values of b to be 0, which doesn't happen in ridge regression or ordinary least squares generally. But through this soft thresholding operator, we know that if the y tilde has a small magnitude, or in particular a magnitude that's smaller than lambda over n, then we set it to 0. So this is this soft thresholding operator, which is very critical for the lasso and is the base of a lot of the basis of a lot of algorithms that are used. In this case, we can re-express b hat Lj in this form. So we get y tilde. This is exactly what the soft thresholding is doing. So if the absolute value of y tilde j is bigger than lambda over square root of n, then we get something that's non-zero. Otherwise, we shrink it to 0. Okay, and then I spoke briefly about most algorithms are kind of based on this soft thresholding idea. There's also other algorithms related to coordinate descent, which is very similar to this soft thresholding idea. Then we moved in the later part of the previous lecture to this analysis. So we know that b hat Lj can be expressed in this in terms of this soft thresholding operator of y tilde j. So remember again, we're assuming that x transpose x over n is the identity here. and that x transpose y over square root of n is equal to this y tilde. And so what this actually means then is that we know that y tilde j is equal to b square root of n times bj plus epsilon tilde j, where epsilon tilde j is normal 0 sigma squared, and the epsilon tilde j's are independent. That's one of these nice properties that we have because we assume x transpose x is over n is the identity. So what that means is that b hat lj can be expressed in terms of the true parameter bj through this soft thresholding operator, and that allows us to do analysis in a straightforward way too. And then I briefly touched on this, but we'll go into it again. We want to choose lambda such that if bj is 0, your estimate is also 0, b hat lj is 0. And we also want to choose it that if bj is not 0, then b hat lj is not 0. So the way that we end up choosing that is you want lambda to be bigger than the maximum kind of noise value of this epsilon tilde j over square root of n. Okay, so we're going to kind of set throughout that lambda over n is bigger than this. And then based on that, you can clearly show that if bj is 0, then b hat lj is also 0, because you've set lambda big enough to ensure that your b hat lj will stay at 0, because you're not going to kind of get above that noise value. And further, if we assume that bj is not 0, one thing I didn't mention in the previous lecture was that to ensure that b hat lj will not be 0, you need to impose this condition that the absolute value of bj is bigger than 2 lambda over n. Okay, and so to see why this is true, let's kind of think this through. So if we know that epsilon tilde j over square root of n is less than or equal to lambda over n, right? And then if we impose the condition that bj bigger than 2 lambda over n, that ensures that the absolute value of bj plus epsilon j over square root of n is bigger than lambda over n. And so therefore we know that b hat lj is bigger than 0 if epsilon j over square root of n is less than lambda over n and absolute value of bj bigger than 2 lambda over n. So what we're kind of saying there is that if bj is really, really close to 0, you might expect, so we only, so in words, I'm just describing kind of what this condition means in words. It ensures that the coefficient value is not too small, because essentially if your coefficient value is too small, you're going to, it's quite natural that the noise is going to overwhelm that. And if the noise overwhelms that, you expect that the lasso will pick 0 rather than picking a non-zero value there. So this is actually, if you think through it, quite a natural condition to expect. And so in that case, so now we have that b hat lj is equal to 0 if and only if bj equals 0. And this is really so this kind of makes our calculation a lot easier. And so what that means is that we can rewrite this as we can kind of rewrite this coordinate by coordinate. And if bj equals 0 and b hat lj equals 0, then clearly, so this is equal to 0, and so we only need to, and then if bj not 0 and b hat lj not 0, then we have that we can see from the soft thresholding operator that this thing is equal to so we know that in that case, E of b hat lj minus bj squared, you're just going to get sigma squared over n for the noise term, and then plus lambda squared over n squared. Okay, so, you know, and so this is like kind of you can think of this as like the variance and then plus a bias. So obviously, you know, we're introducing bias to ensure things are 0. And then we also have this condition that, so note that lambda has to be bigger than or equal to max j so lambda over n has to be bigger than or equal to max of j of 1 to p. So, or to write it in a different way, we can write it as, so, you know, you might look at that and say, well, why not just set lambda equal to 0 or lambda as small as possible? But clearly we want lambda to be bigger than that to ensure that we're only collecting samples where bj is not 0. Therefore, the overall mean squared error, now we're kind of conveniently only adding up terms where bj is not 0. That's going to be equal to sigma squared over n plus lambda squared over n squared, okay? Okay, and so recall that, you know, since we impose this sparsity parameter, that means that okay, and I mentioned as well that you know, we can max j less than 1 less than p epsilon tilde j. This is sort of beyond our calculations to go through this explicitly. This is equal to or we'll say it's less than or equal to 2 times square root of log p. The reason I'm saying less than, because this is actually a random variable, but you can show that with high probability that that's going to be true. That so I'll just say this with, so this is a vague statement, but I'm going to make it just so we can get control over what that value actually is. Has to be less than or equal to s sigma squared over n. So this is, sorry, a sigma here because there's the noise variance is 1, and then plus s or plus 4s sigma squared log p over n. Okay, so and as I mentioned earlier, you can think of this as this is just the variance due to estimating non-zero non-zero coefficients. So if you knew which of the coefficients was non-zero, then you'd get this variance of S sigma squared over n. And then this is the bias since you don't know non-zero coefficients. And so you can clearly see that, as I mentioned in the previous lecture, that we remember that we get this term of P sigma squared over n, which occurs when lambda is 0, because if lambda is 0, you're kind of just summing up all, like you're not going to do any thresholding, and so you're collecting the sigma squared over n for all of the P terms. So this is, remember, like variance of sigma squared over n for each term. Okay, and then, you know, since we have that so clearly, if you know, if S times 1 plus 4 log P is less than P, then gives lower mean squared error. So, you know, as we expected, so therefore, if B is sparse, you get a lower mean squared error. Okay, so I just wanted to kind of wrap this I just wanted to talk about some generalizations as well. So for general X, if X transpose X over N is not the identity, you know, similar algorithms and theory hold. So similar algorithms and theory hold. But we have heavier notation and technicality. The other thing to mention here is that Lasso often in high dimensional So what high dimensional means is that you know, your n is like less than p. That's essentially saying that the number of samples you have is actually smaller than the number of parameters. But in this case, what's cool is that algorithms or theory still hold, provided S log p is less than n. So even if your n is smaller than p, as long as your S log p is less than n, your theory and your algorithm still hold. So, but you know, one thing to note is that note rank of x has to be less than p, because if p is bigger than n, the maximum that the rank of x can be is n or p. So therefore, usually multiple solutions. So multiple solutions that are all valid. So this is something that I can certainly point you to more reading for, and it's a slightly more advanced topic. But I just wanted to touch on the fact that both the lasso and the ridge estimator are often used in the setting where p is actually bigger than n, and they both work reasonably well in that case, because you don't as long as you have like reasonable like low dimensional structure, that p is that the number of non-zero values of b is not that big. If s is not that big, then you can still have pretty good theory and pretty good algorithms. And then the other thing I wanted to mention is that, and I did touch on this in the previous lecture, is that So remember that our original regularization framework had just this notion of a loss function or the negative log likelihood type of scenario, plus a lambda times the regularization term. So a lot of these ideas apply when you consider a GLM, like a Poisson regression or a logistic regression or anything else. But as we say, the theory certainly doesn't work out as nicely and cleanly as the case when when we have this least squares, where this least squares scenario, where we can do calculations and develop algorithms a lot easier. But all of the same ideas apply. It's just that there's a lot more kind of technical challenges there, and I'm not kind of delve into that here. So, you can certainly use, and you potentially will use, the lasso with a logistic, for logistic regression or for Poisson regression. You can still, all of the ideas that I mentioned still apply, but yeah, the theory is a lot more challenging. So now we're gonna just review this whole third module on regularization. So now you should be in a position to do the third homework, and I just kind of wanted to put all the everything we've learned over the last maybe 4 or 5 lectures into a little bit of context. So remember that in our framework, we have our data. So, we're in the okay, so we have our data that's, this typical supervised data here. And I'm going to use this shorthand notation here. So there's 2 shorthands I'm going to use, and then you can also have this third vector matrix shorthand that x is in r to the n by p, and then y is in r to the n. the statistical model that we consider is, we can think about the standard GLM, and more specifically, I guess the linear model. And I've gone through that, and so I'll just sort of point you to see modules 1 and 2 for this, for these, or I won't use that circle, I'll just say. See modules 1 and 2. And then I should mention that, plus some additional structure, i.e. we could have that the L2 norm of, some value is like, of this is small. So this is like, for like ridge, which we'll talk about slowly, or, norm of B0 is less than S, which is what we saw for the lasso. So, in some sense, we have this exactly the same setting we saw before, but we have some additional prior we have some additional prior information about the B. Either it might have a low L2 norm, or it might be sparse or something like that. So the general algorithm and estimators that we considered were of this form. Okay, so where we have, this is the negative log likelihood. Then we have the lambda was this regularization parameter. So lambda bigger than or equal to 0 was this regularization. And R of B was this regularization function. Okay, and in the special cases we considered in this course, for B hat R, we have R of B is, so this is the ridge regression estimator. And then for the lasso, we had that R of B we have that we have this sum of our absolute values. Okay, and then in terms of algorithms, for B hat R, this is convex, smooth, objective. So if Gaussian linear model, then we have that okay, so we have that we have this expression, and then we know that beta hat R has closed form. we have this kind of nice closed form for B hat R. And then, that involved solving a linear system, and I spoke about various algorithms for that. For B hat L, convex but not differentiable. So this presented some different algorithmic challenges. So in that case, in general, there's no closed form, but in this special case where we could see that if we set y in this way, then we could see that B hat Lj is equal to this soft thresholding operator. Okay. Soft thresholding. And this was the basis for a lot of algorithms this was like soft thresholding is the basis for a lot of algorithms, like coordinate descent and others. And just to to also point out that if x transpose x over n equals the identity, we can also kind of write B hat Rj, the ridge estimator. We can kind of write in a very convenient way as well. It's just going to be y tilde j over square root of n times it's going to be 1 plus 1 lambda over n. So note again here that lambda over n denotes regularization, and then obviously the obvious thing here is the least squares estimator also just has this nice form as well. So you can kind of see these see what each of these estimates is doing side by side. So to summarize, equals the identity and x transpose y tilde is x transpose y over n. We have that the least squares kind of does no regularization. It just sort of takes the value of this y tilde. Beta hat ridge, the ridge regression does some this can be thought of as linear shrinkage toward origin, or towards the point of 0, and then and so this is kind of nonlinear soft thresholding. Okay, and so each of these are you can see what the impact is in this special case, and this provides a nice comparison of these three different approaches that we've learned in this case. And then to wrap it up, in terms of analysis, we found that again, we kind of use this notation if x transpose x is equal to the identity, because things are much simpler there, because we can kind of break it down coordinate by coordinate. We obviously know that the least squares estimate has this has this mean squared error. The ridge estimate we found we could get a closed form expression for that as where we get this bias here with the absolute value, but then we potentially reduce the variance times p sigma squared over n. So, and we could think of this as the bias squared, and this is the variance. And then for the lasso, there we get this sigma squared s over n, but then we get a term that's so this isn't a less than or equal to, but it's pretty sharp. So if we assume that beta 0 is less than or equal to s, then we get sigma squared s over n, and then 1 plus 4 log p. So the idea is that beta hat r gives low MSE if the L2 norm of B is small, and that makes sense because that's exactly the regularization you're imposing. And B hat L gives low mean squared error if B's B0 and this is known, as I mentioned earlier, as sparsity. Okay, so this is kind of a very quick summary of the of all the topics that we've covered in the previous lectures on regularization. So this should put you in a position to address all the homework questions from homework 3. But yeah, let me know if there's anything that is unclear from these lectures for the homework. Okay, so now for the remainder of this lecture, we're going to just start to introduce this fourth and final module. I don't think we'll get a time to do a fifth, so we'll stop at this fourth module, which will be graphical models. And so this is a topic that I like a lot, and it's a little bit different from some of the previous topics because we're going to we're going to really try to characterize the dependence of distributions. So I'm going to spend most of today or the rest of this lecture just introducing some ideas behind this and hopefully get to a couple of examples. So the idea here is that so we represent multivariate, so this, multivariate distributions as graphs, okay? And so I'm sort of at this point just kind of like building slowly to the math. You probably won't get too mathematical today. So we represent multivariate distributions as graphs, and so the idea is we're gonna combine concepts from graph theory and probability to provide visual representation distribution. So the idea is that so there's kind of there's two components here. There's one which is graphs, and then two which are probability distributions. So like graphs are nice because they're like, I would say, visually appealing. And that's sort of the main point for that. But, you know, probability distributions are nice because they, well, in this context, they, you know, represent the probabilistic model. They represent the probabilistic model, and in particular, focus here is conditional independences, which we're going to talk about shortly. So you can think about in words, graphs provide so I'd say maybe the best way to describe what we're going to talk about here is that graphical models provide visual representation of conditional independence relationships through graphs. Okay, so I'm gonna so for the remaining about 15 to 20 minutes of this lecture, all I'm gonna do is first define conditional independence, and then it'll be quite a technical definition, but the main thing to take out is the intuition. And then I'm going to give a couple of examples, which we've actually already seen from the first lecture. Okay, so just recall independence. Two random variables, x1 and x2, are independent if okay, so and this is for any sets B1 and B2. So this is quite, there's a lot of kind of set notation here, but all we're really saying is that in words, x2 has no influence on x1, and so example, x1, flip a coin, x2, flip the same coin again. You can think about rolling dice multiple times. There's lots of scenarios where you can think about things where one random event has no influence on another random event. So this leads to the notion of conditional independence. So conditional independence is so we've got p random variables. And then let xj and xk be two of these where j is not equal to k, so we're not talking about the same random variable. And S is a subset of 1, 2, up to p, but doesn't include j or k, okay? So it could be like, for example, x1, x2, and then x3. It could be like x1, x2, and then x3, x4 or something. But S is just some subject. So note the size of S may be greater than 1. So we're conditioning on potentially more than just one variable. Then xj and xk are conditionally of xs if let's be consistent here. And then we're conditioned on xs is in bs. That should equal to okay. And I mean, you're never ever going to use this definition, so you don't really need to worry about applying it, because it's, unless you have very simple cases with only a few outcomes, this is very difficult to actually verify. But in words, what that means is that if you know the value of xs, xj and xk have no influence on each other. Okay, and so this is a little bit more of a nuanced concept, because we're now introducing this SXX. So I'm just going to talk about a couple of examples before we finish here. So I'm going to return to two examples from the previous from lecture 1. So you may not recall, and it's probably worth just going back to this example for this particular lecture. But we have gender bias in admission. So again, I sort of repeat that I'm not sort of expressing a view here. I'm just repeating kind of the conclusion from the study. We found that there were 3 variables. So we had that x1 was the gender, which was a binary variable. So at the time, it was viewed as in the 70s, it was viewed as it was actually the data was stored as a binary variable. x2, we had this chance of admission. This was at UC Berkeley. So this study was conducted at UC Berkeley. And then there was this other variable x3, which was the department applied for. Note that we had x1 and x2 dependent. since females seem to have females had lower admission rate overall, but X1 and X2 seemed independent if we conditioned on X3, the department. Remember that, when we broke things down by department, it seemed pretty similar in terms of the admission rates. And again, I'm, not sort of like proposing a view here. I'm just kind of sort of repeating what's in the data there, what's in that data for that particular study. So here we have that X1 and X2 independent, but we have that X1 and X2 X1 and X2 were dependent, But X1 and X2 conditionally independent given X3. Okay, and so I'm going to draw the graphical model representation without explaining how it comes, because I just want to use this as an introduction to the topic, but we can actually represent this as a graphical model. Because it allows you to visualize this. So what it actually means is that we have these arrows here from X3, and this is what's referred to as confounding or confounders. So we say that X3 is a confounder for X1 and X2. And this is a very common issue when you're dealing with multivariate statistics or probability. You might find that two variables are highly correlated, but there's actually another variable that's actually causing that correlation. That if you knew that variable, then there wouldn't actually be any correlation anymore. So phenomena in statistics. So if you've taken kind of 302 or any other prior statistics course, you may have heard of confounding. And this is something we can actually represent through our graphical model framework, which we'll talk about over the next 3 or 4 lectures, and then talk about how it extends to much more than 3 variables. We can kind of see how that's represented through a graphical model. Let's go through a second example, and this is again an example from the first lecture. You flip 2 coins, and they're fair coins, so I should say they're fair. If the outcome of the coins is the same, you ring a bell. So these are 3 binary variables, so it's kind of in some sense easy to write out the whole distribution. So X1 is outcome of first coin flip. X2 is outcome of second coin flip. X3 is, do you ring the bell? Okay. And so note that what happens here is that clearly x1 and x2 are independent. But if, so this is kind of a reverse of the previous scenario. So x1 and x2 are independent. Obviously, coin flips are independent, but x1 and x3 conditionally dependent given x2. Because if you know that you rung a bell, then you already have the information that they're both the same. So if you know, so for example, if you know that the bell was rung and you know the first coin flip was ahead, that implies that the second coin flip had to be ahead as well. On the other hand, if you know that, this should be x1 and x2 conditionally dependent given x3. Okay, and so graphical model visualization for this. We have our x1, x2, and x3 again. There's nothing between x1 and x2 and x3 here either. But what you actually have is you have the arrows actually going the other way. So in the previous example where we had this confounding, we had the arrows pointing one way. We had the arrows pointing from x3 to x1 and x2. Here what we actually know is, if you think about the procedure, if you know x1 and x2, then that tells you what x3 is. And so this is actually, this is sometimes referred to as, whether it's a paradox or not, it's called a paradox. Bergstrom's paradox. It's also sometimes referred to as explaining away. Because, you might think it's weird that two variables that are somehow independent somehow get an induced dependence between them. And that's exactly because of this scenario that, if you know x3, then x1 and x2 suddenly become independent. And so this is the graphical model representation from that. And the idea here is, since x1 and x2 determine x3, and that's why the arrows are going this way here. Okay, and so basically this is just in the coming lectures, so in the coming lectures, we're going to make this formal. So for today, because we're just introducing the topic, all I did was just, I drew the graphs, and you potentially have no idea where I pulled them from, and that's reasonable. But in the coming lectures, we're actually going to make this, formally understand, how do we go from our multivariate distribution to a graph, basically. And we're going to kind of see that in both of these examples, how you can convert from a multivariate distribution to a graph. So how do we represent multivariate distributions as graphs? That's essentially the what graphical models kind of gets at. And so this gives you a nice visualization of what's going on. And it'll be a mathematically rigorous way of expressing multivariate distributions, which is something that we're going to learn a lot about in the next couple of lectures. Okay, so that's it for today, and we'll go into this in more detail in lecture 15 and beyond. Thank you.